Okay, so as I stated before, Bohr's model explained hydrogen's lines on the EM spectrum, but he could not explain any of the other elements. The behavior of the electrons at this point is still not completely understood, but it is known that they do not travel around the nucleus in a circular orbit. They did figure that out. So in came, a little too fast there, in came Louis de Broglie, and he hypothesized that electrons could move in wave-like particles like they had discussed earlier with Einstein. Okay, so he came up with this figure, and this figure illustrates the orbits that the electrons could have, that they go only in whole number wavelengths around the nucleus. Now remember, we're still trying to figure out exactly where the electrons are located. So he came up with this equation, the de Broglie equation. It predicts the movement of particles, that they all have wave-like characteristics. And then remember, we've used, this is lambda, okay, represents the wavelength. H is Planck's constant again. M is the mass of the particle, and V is the velocity, or how fast it's going. So then Heisenberg came in, and he showed that it is very much impossible to find an electron and know exactly where it is, because by that time it's moved to a different spot. So we call this the Heisenberg uncertainty principle. States that it is fundamentally impossible to know precisely both the velocity and the position of the particle at the same time. In the next slide here, I'll explain that too. Only the quantities can be known in the probability for an electron to occupy a certain region around the nucleus. Okay? So if you look at this, to see an electron, we need to emit light to it. So this photon here. So if we shoot this photon at an electron to try and figure out where it's at, what's going to happen is that light is going to hit it, and that's going to cause it to move at an angle away. Just think of shooting pool. You hit that first cue and the balls just scatter. That's exactly what's going to happen with the photon and the electron. So by the time we figure out where it's at, it's going to be moved to a different position. Schrödinger treated electrons as waves in his model called the quantum mechanical model of the atom. I know that's a really big name. Okay, so we have his equation. Let's go back. Schrödinger's equation applied equally well to all the elements rather than just hydrogen. It included hydrogen, but it included the other elements as well. Okay, the wave function predicts that a three-dimensional region around the nucleus called the atomic orbital. So you can see down here where all these blue dots are concentrated. Each of these blue dots would be a spot where an electron could be, and you can see as you get away from the nucleus, it becomes less and less concentrated. So they are predicting that the electrons are going to be located around the nucleus, which today we find to be true. Okay, so we're around the nucleus. They have started labeling those as orbitals. Okay, so the principal quantum number is going to be n, indicates the relative size and energy of atomic orbitals. N specifies the atom's major energy level, called principal energy levels. And then each energy level can have sublevels. Okay, so just like these bricks down here. So your nucleus would be right down here. So the first energy level away from the nucleus would be N1. It can have one sublevel. As you move away from the nucleus, N2. It can have two sublevels. One more step away, N3, so three sublevels. Another step away, N4, four sublevels. It takes energy to get up to these levels. Remember, as the electron drops back down is when it gives off that emission of light. Okay, each energy sublevel relates to orbitals of different shapes. Okay, so if you have one sublevel, you're going to have an S. Okay, if you have 2 sublevels, you're going to have an S and a P. If you have 3 sublevels, you're going to have an S, a P, and a D. If you have 4 sublevels, you're going to have S, P's, D's, and F's. And each orbital has a different shape, as you can see here. Okay, and you can see here. So your quantum number, or your energy level 1, has 1 sublevel S, okay, and so it has 1 energy level. 2, so yes, 2, energy level 2, or quantum number 2, has 2 sublevels, S and P. Quantum number 3 has 3 sublevels, S, P, D, and F. And quantum number 4, or energy level 4, has 4 sublevels, S, P, D, and F. I just said that. Okay, so which of those sublevels has a dumbbell shape? P, correct. And who proposed the particles could also exhibit wave-like behaviors? Good job.